It can be said that we are all in space, so you can do many things just within this department. You can get great education, you can do top-notch computing, working with the largest supercomputers in the world. And you can also tackle the greatest societal problems that we have related to pollution or climate change. So in a way, this building is a universe of its own.
I really like being here in the Climate and Space Sciences and Engineering department at Michigan because we're a really big space physics group.
I specialize in numerical simulations of magnetic solar eruptions.
I specialize mostly working on comets.
I specialize in biosphere-atmosphere interactions.
And I study solar wind and particles that are carried in solar wind.
My specialty is the origin and evolution of the planetary atmospheres and planetary habitability.
Well, one of the strengths that we have here in the department is that we span across science and engineering, and that's a great asset to our students because they learn the scientific foundations, but they can also learn about engineering.
So being a student in the College of Engineering means you have access to a lot of laboratory tools and computing resources to do the things that you're learning about in class.
Not only for students, success, but also for faculty. I think having access to the scientific expertise and engineering expertise available within the College of Engineering, I think is vital to the success of this department.
We're more than 50 years into the space age, and we still have some real fundamental mysteries about the sun. Really like to understand what the sun is doing that's so good at heating things to high temperatures. Those high temperatures lead to this supersonic solar wind. And that can have societal effects at Earth. It can disrupt communications, radar, GPS. So we want to understand the underlying basic physics, and we'll better understand our universe. We also want to be able to predict whether these space weather events can harm society.
Michigan has a very long history of numerical modeling for space weather. We are the developers of the BATS-RS, which is a code, which is a big magnetofluid code, and has been coupled with other codes in this larger system called the Space Weather Modeling Framework.
So Space Weather Modeling Framework is one of the leading numerical modeling framework in the world for space weather research. Our nearest space environment is a very complicated system, so only modeling framework like Space Weather Modeling Framework will be able to capture the coupling and the feedback in the system.
I have the belief that scientific solutions are probably one of the most impactful ways that we can protect our environment and also improve our relationship with the environment. And I think that one of the best ways to do that that's relevant to the world today is through climate science.
So my work in atmospheric dynamics does encompass understanding tropical phenomena like the Madden-Julian oscillation, El Nino, and tropical waves. And I do simple theoretical derivations, and with this improved conceptual understanding, we can use model analysis and observations to see what these systems are, and then go back and try to improve our theoretical understanding.
I study how ice sheets and glaciers are changing in response to past, present, and future climate change. And it's been interesting over the past decade or two because we've seen changes that we've never seen before in Antarctica. We saw ice sheets change in ways that we didn't expect, that models didn't predict. So the Larsen B ice shelf, which had been stable for 10,000 years, in 2002 it completely disintegrated over about 6 weeks. And so we're seeing these very dramatic changes that we're still trying to understand.
I chose CLASP when I came in here because there is a wide variety of research interests that are represented by faculty in the department. Right now, for instance, I'm looking at atmospheric dynamics, so the high pressure systems that I'm looking at. I can talk to dynamicists in the department like Christian Jablanowski, for instance.
So my research looks at variable resolution measures. So what we mean, we zoom into the region of interest with very high resolution measures that gives us fine scaling, and then we can really resolve features like the thunderstorm structure in a hurricane. One other aspect is, we can put these measures statically over a region of interest, or we can also let these measures move, and we call that adaptive measure refinement. And that is a very sophisticated way of tracking a feature as it evolves and moves. And I will be basically a beneficiary of measurements that we are taking here in this department with the Cygnus mission, for example.
And so Cygnus is the first of its kind mission. It's a constellation of small satellites in low Earth orbit to measure the winds and hurricanes. And it's the first time that NASA is essentially subcontracting out the management of the entire mission outside of the NASA infrastructure and letting a university run the entire mission, which is what we're doing now. And all of those things are motivated by trying to expand the community of people that do space missions. And we've been pretty successful at it so far.
What we do in our group, for example, is we've designed an environmental chamber where we can actually simulate the Martian atmosphere, the near-surface Martian atmosphere, in terms of temperature, pressure, and humidity. And especially with the humidity part, this is one of the few in the world that can do that in the entire range of the Martian conditions. And we use that to also develop instrumentation. We are calibrating the current relative humidity sensor for the Mars Science Laboratory, Curiosity, and we're also working on calibrating the relative humidity sensor for the upcoming Mars 2020 mission.
Yeah, so Mars 2020 will take like the next step by not only seeking past habitable conditions, but also by seeking past microbial life itself.
And so the study of the planetary atmospheres is extremely important, not just for our own solar system, but for the new planets that we are discovering, especially the habitable zone planets, but also big planets like Jupiter and Jupiter-sized planets that we're discovering in other solar systems.
It's amazing to see just the whole breadth of problems that we still haven't fully understood, and like how we're still able to kind of like grasp the essence of these things and like communicate them to the public, And I think that too, to me, is one of the amazing things about climate science.
I think the challenge of space exploration really inspire students to get excited about technology and coming up with new innovative solutions. That's how we develop new technology, new ideas, just dreaming and then going after that dream.